which is actually equal to the determinant of a matrix that has partial derivatives of x and y with respect to u and v. And in fact, this could be related to something that would have been seen in 169, because one operation that was covered in 169 that is related to determinants is the cross product. What is the cross product useful for? Area of a parallelogram. So if you have a rectangle in xy space mapped as dx and dy go to 0, it's roughly a parallelogram in uv space. So the area of this parallelogram can be computed using a cross product, which is actually related to a determinant. So we're going to see how all these things connect when we get to this part of the course. So during the last part of the course, we get into vector fields. So vector fields are functions where at each point what you get is not a number but a vector. A function that would take 3 variables in, turn 3 variables as output. So if I were to graph a vector field, say in 2 dimensions, at each point I would get a vector. It could be something like this. And this is a nice way of visualizing a vector field. It's computing a vector that you get at various points and then plotting it. Who knows what shape you're going to get. If you recall the fundamental theorem of calculus, we have integral of a derivative from a to b is just f of b minus f of a. So this gives way to the fundamental theorem of line integrals, where if you have a function that's defined along a curve and you want to compute, so instead of a function being defined along a straight path, like the x-axis for instance, it's defined on this curve and you want to compute the area under a graph, but only along the curve, then what you can do is use this fundamental theorem of line integrals, that the gradient of f, of a function f, evaluated at a position vector r of t, which would describe this curve, dot product with r prime of t dt is equal to something that's reminiscent of the fundamental theorem of calculus. It's just going to be a function f evaluated at your position vector evaluated at the last value of a parameter t minus your function evaluated at the position vector for the initial value of t. So this corresponds to the f of b minus f of a that we see up here. This gradient that we have here corresponds to this derivative. We had to do a change of variables to get this whole thing in terms of t. But during the last third of the course, we're going to be seeing several integral theorems that are all related to the fundamental theorem of calculus. And they're actually listed on the last page of the notes. Green's theorem deals with this situation where you have some region, two-dimensional region sitting in the xy plane. So what it does is it relates, I'll call this region D, and this boundary curve, this is a symbol that's commonly used for it. It's a partial symbol again, boundary of D. So what Green's theorem does, without writing the formula for it, is it relates an integral over a region, the interior, to an integral over the boundary of a region, which would take a lot less work to compute. Just as here, the integral of a function over some interval is related to the values of a function at the endpoints. So it's the same idea. Green's theorem happens to look like this. This is the integral over the region, where dA is meant to indicate that we're taking infinitesimally small areas of this and adding them up. We're integrating over a two-dimensional region. It's equal to the integral over the boundary, which is just a curve of x plus q dy. So notice, when we're talking about the interior integral, we have derivatives. Those functions are no longer differentiated in the integral over the boundary. So on the last page, there's several theorems like that we'll cover towards the end that have this kind of relationship to one another, which means they're actually direct generalizations of a fundamental theorem of calculus. So what we'll cover from the very last topic of the course is using a different notation to describe all of these different kinds of vector fields and integrals of them that are called differential forms. They're only covered in Marsden. So after we already have the fundamental theorem of line integrals, then we have Green's theorem, Stokes' theorem, and the divergence theorem, that all these can actually be summarized into only one result that's actually very simple to write, that we have that this is called a differential form. The integral of a differential form over the boundary of a region is equal to the differential of a form over the interior of a region. All of these theorems, there's actually going to be 6 all told, are actually saying exactly the same thing, and that's what we conclude at the end.